And hello, students. Professor Peter Gregory here with video solutions for 6B, homework 6B, which would be 631, 630, 631, 3, 8, 9, 41, 2, and 3. And these have to do with really working over what we would think of as confidence intervals. Whoops, that's pretty fat there. Let me get rid of that and get a thinner pen here. Don't know where that came from. Okay, so this problem that we're looking at right now, we'll take a look at 630. Okay, I'm going to go into this a little bit deeper to explain some of the things that are going on in the book. You're going to need some guidance in some of these problems because I see that the solutions made choices that might leave you a little bit ambiguous, or they were ambiguous, the questions with which form of Z or T that you should use in the formula. Okay, so when we use when we were doing confidence intervals around population means, we'll have a choice of T or Z. We're going to use Z or T. What is the difference? When do we use one over the other? Well, Z is when N is greater than 30, okay? And T obviously is less than or equal to 30. Now, this is a rough rule that I believe if we look at it as we go into some of these problems, wasn't adhered to. They were some of these problems would give you a problem if you tried to use a Z. It wouldn't take the answer, I believe. I think you're going to need a T. But in this problem, we're going to go over this fairly deeply because I want to show a few different parameters or behaviors or attributes of doing these kinds of problems. So the problem here is a survey of 50 young professionals found they spent an average of almost $23 when dining out. Now this must have been from very long ago, or that is probably per person these days. Okay. You can go out and have any good dinner and split it for $11 a piece. I don't know where you're going to get that. With a standard deviation of 13.6. Now, the coefficient of variability here is something to think about. We haven't talked about it too much here, but as we're drawing, we're going to go back to raw data. Now we're not going to be doing sampling distributions. Okay, so right now we're doing a sampling distribution. Let's go back to raw data. Okay, and we'll use it there. If you look at the mean of something, they say that it is, let's just, yeah, so the data says that it's $22.98 with a standard variation of 13.06. And we can take the coefficient of variability, and you can see that your standard deviation is almost half. It's getting on to half of your mean. Okay, so it's your standard deviation by your, let's go by sample mean. Actually, it would be your population mean, but for the sake of conversation here, it would be equal to standard deviation by mean. This is what I meant to draw. Okay, all right. And that's almost 0.5. I mean, if we're to calculate it, I don't want to take the time to slow it down too much here. But look at the variability that you have here. So this, again, can continually tease out what's going on in the data here. This is a fairly large standard deviation, okay? Because what would that say? That would say that it's 22.98. Let's call it $23 minus 13. Okay, so your standard deviation is $13 here. Your first standard deviation shows up here, second and third. Okay, so keep in mind what's going on. That's pretty wide data. Okay, can you conclude statistically that the population mean is greater than 25? Use a 95% confidence level. So let's punch some numbers in here. I set this thing up to save time. What's alpha? Alpha is going to be equal to 1 minus 0.95. We know that it's 13.06, I think it says over there. All right. Sample size is 50. Okay, so what does 50 tell us? It's 50 is greater than 30, but I want to show you something here because this problem, I believe, I only got the right answers when I was using the T value, not the Z value. Okay. All right. So even though the rough rule of thumb is that T, when N is less than or equal to 30, I'm going to show you that the tables, if you go out on the internet and you just grab some tables, or if you look in the back of the book, I don't know what the back of our book looks like. I've never looked in there. I just run over to Google while I'm working on the computer, and I download, or I just take a quick look at it on the screen as to what the t-value is that I need, and then go back again. So, but we're going to compute that as well, okay? Because you can compute it or use a table, and when you compute it, you're going to get a higher precision on it, right? So, what's the sample average was 22.98, 22.98, okay? All right. So, I had to use the t-value to get the correct answer here. So, what is the t-value? Okay, it's different than the z. The t-value only depends on two things. I'm going to try to help you remember some of these things. It only depends on alpha, either the level of confidence or the level of significance. Remember, alpha is the level of significance, and it's just equal to 1 minus the level of confidence. Okay, so they play off each other. We're going to see more of that in hypothesis testing in chapter 7, which is related to this. So you do want to get this down and figure out. There's a matrix I'll put up here to think about how to do these problems. How do you sort out these problems? Okay, so the t-value. Okay, so the t-value is, we can either use t dot inverse, and we need to use the probability, where, just to remind you, go back into the book, and we're doing it this two-tailed with the t. Okay, so the t distribution has a center point of 0. Okay, and we need to use t up here. Okay, and it's a two-tailed type of approach on this. So we need to split the alpha. Okay, so the alpha is going to be 0.05. We need to split the alpha 0.025 up here and 0.025 down here. And so we want to get the t of this, okay, which would be what, 0.975, if I'm not mistaken. Okay, so we need a t-value at 0.975 of the level of confidence there. Okay, so we're going to use t equals t dot inverse of what we need to know this over 2, and it needs to know the degrees of freedom is going to be equal to 50 minus 1. Okay, and so what we get in there is we need to put in, now what I had done here is I did not put the 1 minus. It doesn't matter. Don't want to confuse you, but we're going to put a 1 minus in this, right? Because of what I just said, we really used 1 minus, 975 is 1 minus alpha over 2. Okay, so just think about it when you use this t inverse. Some of this is a bit of memorization and pattern and repeat, okay, until it sort of sinks in. We never did the derivatives of this or derivation of this. Okay, we're just going along with this. So when we use this formula, we put in the alpha. It's really 1 minus alpha over 2. So that's why they called it the probability. So technically we're putting in there 0.975, and we want n minus 1 there. So we get a 2.906 calculated. Okay, so that's using all the precision that the computer has to offer. Now, what I'm showing down here is that was, I generated my own table. So you can do this. I want to just show you all the things that, as you start getting more fluid and fluent with Excel, that you can do here. I just ran a t-table down here to show what happens for the number of samples. What happens to t? Okay, so let's look at t. So you can't start with one sample, because t depends on what? It depends on alpha, okay, the probability or the alpha, and it depends on how many, and that's the degree, of confidence that we want in our confidence interval. Okay, so we're just deciding that a priori, and we can generate t. And the only other thing we need is how many samples are we going to take, or did we take? All right, and since it depends on n minus 1, and degrees of freedom, it depends on the sample count minus 1. We can't have n is equal to 1. You have to start with 2, because it doesn't work for 0. There's no such thing as a 0 t statistic where you're taking 0 samples for one sample. Doesn't compute. What's one? In other words, what's one sample? I mean, that's it. That's your average. That's everything. That's all you know. Okay, so you at least have to have 2. And look how this starts narrowing down. Okay, so if you start looking how it diminishes so quickly, to take 2 points, you're going to have a wide, very large t. Okay, so t, the larger it is going to increase our confidence interval. Okay, and it decreases asymptotically like this. Okay, so it starts out here, it drops really fast, and then it runs off asymptotically to the x-axis. never touches like so many other things we do. So I went down to 50, okay? And I got a 2. Did I round that at all? No, I did not. So for 50, our T should be 2.010. Okay, 2.010, which it is. We just have to, it's just showing one more digit here than we need. Let me take that down, and that's why you get 2.010 there. We're going to use that, and I'm just using Excel to visually round this, but underneath Excel, it has not rounded, it has not concatenated, it hasn't done anything to this. We still have many digits of precision, okay? Okay, so now we can compute our error. How is our error computed? Okay, two different ways. We can use the confidence dot t, okay? We can use that, or we can long form calculate it. Let's do both so you see what's going on here. Okay, so I'm going to do equals confidence dot t, because you need the t. There's norm and others in there, okay? And it wants alpha, so they're taking some of the work away. They're doing some combinations here. Okay, so they want alpha in there. They want the standard deviation, which is and that is of the sample standard deviation. And they just say, give me the number of samples there. Okay. Okay. So the way that we can calculate that, the way that this is actually calculated in the book, you want to be able to do things long form as well as this quick form. I'm going to type it in because I don't want to start getting it. Well, I guess I should write it here. Okay, so your error is, what you're looking for is the mean. Okay, so remember what we're doing here? Plus or minus this error. Okay, and the error is going to be t. What they say is alpha over 2 n minus 1. They just try to remember what the parameters are that you're using for t here. Okay, and it is multiplied by the sample standard deviation divided by the square root of n. Okay, so we're going to run the error over here using the equation. Okay, so that's just this part of it. We haven't plus and minused it from x yet. We're going to. Okay, so this is going to be equal to our t star standard deviation over square root of 50, and we get the same number. So that's how you use the confidence.t. But for the longest time, you want to run both of them. I mean, this is just my suggestion because it takes a while to remember this, and it's a lot of repetition. It really takes practice to do this. Okay, so we're almost there. Now we have no trouble with this. So then we take our mean, our sample average, and what do they want? Let's put the minus first. So it's going to be minus the error. Remember, plus or minus the error. So let's just minus the error, and this is going to be equal to our mean plus the error. Boom. Okay, we're almost there. Okay, so what this says is we have a mean. Try to draw this compact here. We have a mean of 22.98, right? And the confidence interval goes out to, now remember, our standard deviation is 13, 13, 13, and another 13, 13, 13, and another 13. So this sets up the scale of our graphs, right? So let's see. So 22, what do we say? 23 minus 13 is about 10. So this mark, the first standard deviation is about 10. Okay. First standard deviation. Okay. And so this shows us that this is the issue that I was talking about as far as the coefficient of variability that we have here is so large that our confidence interval, if you draw it to scale here, is like 19 to 20. I'm going to really rough this out. 19 to 27. I'm really rounding on this. Okay. So that would be like 19 to 27. Like that. That's 22. All right. So it's minus 5. It's be 22 minus 3 point, so we have 19.2 and we have 26 is just above it. Okay, so if we add 13, that would be 36, because this mark here would be 36. I hope you can see it. I'm sorry, I'm trying to draw it compact here, but what I'm trying to do is I'm using the curve, the look of the curve here. Okay, so to draw that better, I'm using a magnifying glass now. It would look like this. I'll draw it larger. Okay, draw it even larger. The roll off here. This is I'm going to make the first standard deviation. I'm going to show it to the left here. This is the top of our curve right here. This is our average, right? And I want to draw. I'm like expanding it. I'm magnifying it. Okay. So there's our plus and minus the standard deviation, and so that was, what did I say, 10 and 36, 30, 36. Okay, 36. I'm just trying to draw this to scale. So we're only going 22. This would be like 20 here, and this would be about, where's 30, like here, something like 22. Okay, so this is about 20. This is about the scale of our confidence, right? And this problem, I'm showing you a lot more than what this problem is talking about. I'm showing you this other dimension where it's so variable that our confidence interval is now just between here and here. That tells us what? 95% likelihood that the mean of the population lies between these bars. Okay, it's 95% confident that the actual population mean resides between these bars. If you took 100 samples, you'd be wrong 5% of the time. Keep that clear. Use this as a personal judgment. All right. Could you live with being wrong on a question like this, or a real world solution 5% of the time? Maybe we would need to go to 99%. Okay. And what would that say? That would say that these would widen out. Okay. All right. If you have to be right, if you could only afford to be wrong 1% of the time, right? Then you have to widen the confidence interval here. Okay, so that's, I've shown you quite a bit more. I showed you the coefficient of variability that you almost always should look at this data, because we're assuming that it's normally distributed here. I ran a t-table here. Okay, so I ran a t-table down to 50. Okay, and we ran this as a t. Okay, now if you were going by the book, I believe it might have thrown you off a little bit, because you would have said 50. I'm going to go use the z. Okay, the z-score, not the t. Okay, let's look at what that would be. Okay, so I think this will work. Let me just show you. I ran this out a little bit earlier. Okay, let's see how different it is. Like, we have this question now of z versus t. They told us, 30 below, use t. N is equal to 30 below, use t. What if it is above 30, go to z? Well, here's a problem that they gave me that I had to run it both ways before I figured out what they were looking for there, to be honest with you. So that's why I do make these videos, just to catch things like this. And let me just flip this over to show it. Okay, so what I did here, I get the right t? Yeah, I got the right t there. Okay, so what I did was, this is t or z. Okay, so this is a column where I use the t distribution, and this is where I use the z, like a normal distribution. Okay, let me center them up. And so the t, back up here, 2.01, that's just this rounded up. Okay, and our z is a little bit less. And if you remember how you run this, it's virtually the same. It's virtually the same. We don't have to calculate t here. We do t off of a normal z table. Okay, so z of 1.96, if you round that, these are both, this is the t for 0.95, and this is the z for 0.95 confidence. Okay, confidence level. All right, so we calculated the error. Okay, so this is the error when you use t. This is the error when you use z. Notice how close they are. They're within 2/hundredths of each other, right? And then what I did is I ran out the confidence intervals using both of them. Okay, so this is a way of thoroughly looking at this problem. Okay, let's not just leave it, oh, okay, they just wanted the t. Let's look at what is the difference between z and t, and using this right now. Okay, so let me bump that up. It came off. I'm going to 4 places on that. Okay, for some reason they're really rounded. That's kind of weird. Okay, I thought they were going to have more digits involved with that. Okay, so what can we say about this? Let's look at what percent is the t versus the z confidence interval. Okay, all right, follow me on this. So, again, I'm doing this to demonstrate you can play around with these numbers. Don't be limited to what it's asking for you here. Once you get this number, Where'd I go here? Right. Once you get your number here, think it out. I mean, it's like I'm trying to help you read between the lines in the book. All right. So what's the difference here? Let's look at. We're going to take the size of the using the t is just going to be equal to, and this is going to actually 2 times your error, right? Okay. So it's just 2 times your error, one to the left, one to the right. Okay. And we're going to divide by 2, and obviously the 2's would cancel out if we simplified this. Okay. We're looking at the length of one versus of t versus t versus z. Okay, so what is it? It's 0.2531 larger. That's an error on the error. Okay, that's if you use, if you really should be using t as they did here. This says if you ran to z, you're going to be off by 2%. It's 2% smaller. It's actually 2% smaller than the t. Just to give you an idea why there's these two different, these t and these z's. All right. Okay. So the other part of the question said, let's finish this off. Said, greater as there's another part. I thought there was another part to this. Can you conclude the function is greater? Oh, it's greater than 25. Oh, okay. So that's part of the question is, can we conclude that the population mean is greater than 25? Okay, so what that was saying is, here's what we just figured out. Here's 22.98. And again, I want to blow out, I have to scale this. I'm trying to keep it to scale here, which is difficult because that coefficient of variability is so high on this problem. Okay, so see if I can grab that whole thing at once. All right, I'm going to try to magnify it a little bit. I'm just going to mark it here, here. Using the t, we got 19.2684. 19.27. And up here we got 26.69. Okay. So these are just an error down this direction, this big E that we just calculated. 1 E there. And they said, can we say that the population mean is greater than 25? So 25 is right here. Okay. Why can we not say that? All right. Because our range includes the possibility that the population mean could be all the way down here. We have under the rule that we use 95% confidence interval. We said that the mean could be all the way down here. Okay, so that's why we cannot conclude that the population mean is greater than 25, which would be this direction. Okay, right. So we do include part of the scale here says, it could be greater, but more of it is actually way down below it. Is that it could be pretty far down below. It could be as low as 19.27 at the 25% confidence level. Let's call it level of confidence. Okay. Okay, so now we have problem 631, and this is a proportion problem. All right, so we're going to calculate the error differently. The standard error that we're going to use is going to be calculated differently. All right, so we did one of these in class, or I did this one in class, I think, or one like this. Okay, so confidence interval for a proportion. All right, so the idea here is the error, okay, this time, I'll write it down here, is the error is going to be equal z of alpha over 2. Okay, and the reason that it's alpha over 2 is symmetry, just like when we use the t. All right, what we're going to do is it's two-tailed, okay? So we remind ourselves by the nomenclature like they use in the book, z alpha over 2, okay? So what is the level of confidence is 95% again in here. Okay, so level of confidence, the LOC is equal to 0.95. That's how we get alpha, okay? So alpha is going to be 0.05, all right? So obviously alpha over 2 is going to be equal to 2 is equal to 0.025. Again, all right, at least they're keeping the numbers the same, doesn't throw us off. We can keep marching along with these, all right? Excuse me. So we need to know when we do this, we need to know z alpha over 2, and we want to know up to and including this point. Okay, and this is why we're going to do, just like the last problem, we're going to end up doing a 1 minus alpha over 2 in our equation here, which will give us the 0.975 point at this point. This is why they do alpha over 2. It's a little bit of a brief explanation, but think it out or just take it. You can see a little bit of why we're doing that. Okay, so the book does explain that. So alpha is going to be equal to, it's kind of funny, we do alpha and then we go get the confidence level, right? Okay, so alpha is going to be equal to 1 minus 0.95. There's our, oh, try that again. It's equal to 1 minus. Okay, I forgot the minus there. Okay, what's the sample proportion? 230 1/8. So what is the sample proportion? Does anybody know what 1/8 is? It's equal to 1 over 8 is 0.125. Okay, and the sample size of 230, I think we put in there. Right? Okay, so the level of confidence, I think what we really want to say here is let's call it the level of confidence is again 0.95, just to remind us, the z value. Okay, so how do we get the z value here? Okay, so we've done this before. This one was norm.s.inverse, right? Is 1 minus that over 2. Oh, I didn't put the dot s in there. I was wondering why it didn't give me the shortcut. There we go. Okay, so 1.96. You kind of get used to using 95, all right? And what we could do is you can create a table of what the z's are for these. Okay, so I'll do that really quick here. So let's say we want 0.80, 0.90, 0.95, and we'll go to 0.99. Just 3. And just to give you an idea of what the power of Excel is, you can just see the comparison here. So the z, if we do it the same way, all right, we'll put the alpha in here, is what? It's going to be equal to 1 minus that, all right? This is the way that they tee it up in the course, so we're going to hold to the convention. So what's a z? It's going to be equal to the norm dot inverse of that over 2, and we want the upper end of it. All this does is gives us the positive version of the z. That's all that does. All right. So here's our different z's. Z gets larger. Okay. So as our confidence level of confidence goes up, the root of the error is in the z. Okay. So we have this compound. The error is made up of on here z, p, and n. Okay. So we're doing proportions now. So how do we do that? The error is equal to z over 2, just a reminder to ourselves, times what? The square root of p times p minus 1. That's an interesting setup there, over n. Okay? So what you can also do is look at this population. I think I ran this through in class. Excuse me. So we're going to want to remember this for a later problem. It's a very, very minor line that they put into the chapter information that we're going to take advantage of. And it's kind of cool. You're starting to get good at this. You're starting to get powerful with it. And we're going to start making these assumptions and go, okay, we'll take the worst case there. We might not need to know exactly. I can look at this problem. I might not know exactly what the problem is. I don't know the numbers behind the problem. I don't know what the proportion is. I'll use the worst case that there possibly could be. We're going to use that later on. Okay, so for different P's, okay, I'm going to plot this. I did this in class about a week ago. All right. So I'm just plotting the p times the p minus 1 to see what that does. Let's just look at what that does. So here we're going to do what if our population or proportion rather, our proportion was 0.05. I'll try to do these in steps, okay? So we're going to go up. The proportion went from 5%. No, actually, let's go from 0, okay? And then we're going to do 0.05% or 5%, 5%, and zero point 0.1. That's 10%, okay? And let's go up to 100%. One more. Okay, there we go. And so what is going to be P star P minus, no, 1 minus P, 1 minus P. What does that thing even look like? And this is kind of neat, all right? So this is, again, how you tease out the behavior of some of these equations, all right? Okay, so let's type that out. It's going to be equal to that star 1 minus that. Okay, I'm going to want that when I plot it, all right? So let's look at what this thing looks like. It's almost a half circle. Okay, so if you look at this, let's bump this up a little bit. Let's make them all even. All right, we'll go to 4 places on it. Let's go to 1. This is like a movie because I can change things. So just to take a look at it, the most significant digit here goes from 0 to 1 to 2 back to 1 to 0. It's a symmetric issue because we have p times, that should be 1 minus p. I beg your great pardon there. That should say 1 minus p, not p minus 1. All right, sorry about that. But anyway, we'll plot this. Okay, let's plot that. See what it looks like. Before that, before I do that, I'm going to show a few more decimal places. Okay, so give me another one, and we can kind of see that this thing goes up and it goes down again. All right, so as your population's way over on the sides, on the edges, where it's low probability or very high probability, this compound formula here, which I will fix, as I said, I beg your greatest pardon on that. Let me just fix that. P times 1 minus P over N. Okay, now it's reading right. So we're going to plot this now. Sir, let's really do for recommended here. Yeah, sure, we'll take that. Okay, that's fine. Quick and easy. All right. so this is an interesting behavior of this formula that it peaks out where. Okay, let's stretch this out. I'll get some more. All right. So it goes between 0 whenever the probability is extremely low or very high, as in 0 or 100%, it turns out to be 0. The effect on the proportion isn't helping. It doesn't add anything. Not that it doesn't help, it doesn't hurt. It ends up zeroing out our error. Okay, so if you have a 0 or 100%, it's not interesting, right? So that's not really interesting. There is a rule of thumb that your p times n should be greater than 5. Should be greater than 5. Let's say greater than equal to 5 when they're doing this. I don't know if the book reports that out, but we'll take a look at what it means for this problem here. Okay, so we can see, and as I said, we're going to use this later on. Come on, just move. Close that out. Everything's going on here. We're going to use the fact that P of 50%, if you have a 50-50 shot of something happening, it has its highest error, right? That number is going to be the greatest. Okay, so now let's think about n. Okay, as n goes really, really high, a million cajillion here, right? What happens? This thing goes to 0. The highest it ever can be is whatever that value was. 0.5, it's 0.25, of course. So this would be 0.5 times 0.5 is 0.25, right? It maxes out at this point. This error maxes out with a little small n. If you have a small n, okay, it doesn't damage or doesn't diminish the numerator that much. But if this goes to 1,000 or a million or a lot more than that, this turns this factor into 0 again, and this zeroes this thing out. So what does that say? It says you're getting pretty close to estimating the population. You're taking so many n's that you're getting out there toward the population again. It's almost like you've got a pretty good sample. It's not, the more n's you take, the less likely it is that you have an odd an odd sampling error. Okay, remember, because there's sampling error and non-sampling error. Sampling error is purely due to the variability of the data, the pure inherent uh, random variable that we have. What it's going to come out as the the non-sampling error. Non-sampling error has to do, if you take, especially think about it, if we take a poll in the class and we have about 10 people in the class, right? We're going to get non-sampling errors. Let's say let's look at the average salary of the United States, and we're going to use 10 people that who are for most of the part are seniors. You're seniors in college, right? What's the problem with that? Obviously that's non-sampling. We're picking a group of people that are working. You're sacrificing to go get a good high-paying job. You're not there yet, so your salaries aren't going to reflect those in the United States. Okay, so you want, when you're looking at such a huge population as whatever it is, 325 million, I think, or 350 million, right? And you only take 10. We've picked from a very homogeneous sample that is off the average. I mean, you can't really pick 10 people in the United States. You'd have to know. You'd have to go get one, Fortune 500 company that is from, what's the biggest Fortune 500 company? Walmart. So you go to the highest paid person. Let's assume they're in Walmart. I mean, by a long shot, they're over 500 billion dollars. Their sales are greater than $500 billion. Okay, so maybe we'll take a look at the Fortune 500 list and look at what their profits were. Look what earnings were on $500 billion, $500 billion worldwide they're taking. Take a look at what their earnings were, and you're going to be pretty interested and keep moving down the list. It's very low. I think it's like 2% if you take a look at it. All right. So what's held back after they take the taxes and everything else out. Okay, so this is providing more of a field. This is the field that you really need for this problem. I mean, this is why we're even studying it, is to pick apart a problem and take a look at it. All right, so we ran a bunch of z's over here. Okay, we always use the z when we do proportions. Okay, how are we doing here? We've got a z value out of that. Wonderful. What's our standard error? Okay, so I think I could just say our standard error is going to be this star. I can use a square root here of what? Of p. Sample proportion is that star 1 minus that. Let's make sure I get this right. Over 50. Or 230 rather. We did that already. Square root of that. That looks good. Let's see if it looks reasonable. Our standard error is such. So we had 0.125 plus or minus about 4% of 0.125, or right. It's 12.5% of the population plus or minus 4%. Okay. Okay, and now we're home free. We just have to take the proportion, not minus the error equals the proportion plus the error. Okay, and that should fill in this slot very finely. And they ask, as 0.15, I guess you have to fill in, since 0.15. Okay, so they ask you about 0.15 up here. Oh, can you conclusively say that the proportion who use cell phones primarily for the email is less than 0.5? Okay, so if we put 0.15 on here to draw it, okay, standard. Okay, so we ended up with, we'll do it in percent, 12.5%. Goes down to 8.2%. 2%. That's 4, right? It's 4% difference. That's about what we have here. And it goes up to 16.8. So again, we have this 0.15 ending up right here. It says, uh, can you conclude seriously the proportion who use cell phone for you is less than 0.15? It's kind of laid up the similar way as the previous equation, but now they're saying less than, not greater than. The last question was, they said, says can the proportion really be 0.15? Well, no, because there's still likelihood that it's greater than 0.15 up here. So that would be, you cannot conclude. All right, on to the next problem. Okay, on to 633. This is an A-B test, okay? So we have two subsets within the larger set of samples we take, and it's scarce data. It's not going to be very high data. If you take a look, there's only about 24-ish or so counts of liberal arts in this study, and just about the same number of university type respondents here, whatever it is. So we're looking at the median SAT. And the point here, another comment that's sort of just glanced over in the book, so you have to read the fine print, is what we do for the mean applies to the median. We can treat the median the same way as we treat the mean. Anything we do with the mean. Okay, so here, we'll have to pick out some data for the liberal arts. We'll have to pick out some data from the university, and we're going to compare them. We're going to run the confidence intervals, and one of the questions here says, is this is for the SAT, okay? And they're going to see, is there a difference? Is there a notable difference, a substantiated difference between university median SATs and liberal arts median SATs? Let's go find out. All right. So this is a nice real problem that we have here. So the sample mean is going to be alt MUA is your. These are already sorted out. This data was already sorted out. This, by the way, these problems, this data approximates what you pull down out of the problem when they're fed to you. Okay, this data where you get it from would be the raw files. There's a set of raw files that go along with the chapters, and every one of these questions that we're looking at ends up in the back of the book. And the problem number 33, if you go back to the end of chapter 6, it's problem 33. I don't know if I ever mentioned that or not, but it doesn't really matter. You don't have to go there. There's nothing to see there unless you want to run the full data on it. Okay, so when you get these questions presented to you, you click on this little icon over here. Now this is just a screenshot, so it's not live, but you just click on that icon and you pull the data, download it as Excel, all right, whatever they give you. So this might be a little bit actually more with more flourishments in here, a little bit more information, whatever else. Okay, so we need the sample mean for, we are doing liberal arts here, right? So I'm going to grab this range here. Be careful not to pick up anywhere else. I'm not even quite sure how many there are there yet. Okay, so the mean is 1256 on SATs. That's the median. Half of the students that applied or were accepted, whatever the problem is here, half of them will be below that, half of them will be above that. Okay, so it's different than the mean. Sample standard deviation is equal to the standard deviation of, we're using the S now. Remember, this is the time when we use the sample standard deviation here. We need the numbers. We just pick up the same range here. We could have named this range. I didn't do that. Okay. So the sample standard deviation, just make sure that looks through 4 through C. Yeah, that's good. Just don't double check that. Okay, so equals count if. We can actually just put the number in here. We can do a count if, I guess. Count if use this again. This is overkill. Could just look at it. All right. In that range is equal to. Now you have to spell things exactly right, or else it will not work. Okay, we got 25. Does that make sense? 28 minus 3. Yeah, okay, good. All right, and then the alpha is going to equal 1 minus 0.95. Okay, what's our t value? Okay, so we can do equals. Let's do the other first one over here. So let's do this. Let's do the sample mean of this is alt MUA of everything that says university here. And again, these were pre-sorted for us, filtered and sorted. Okay, so that's enough. All right. Let's look at the average. Okay, so the university is a little, the median is a little bit higher than the university. Okay, is that significantly different? Let's just go find out, right? Standard of data, that very same data. The variation is quite large, and that median's more. Okay. So again, from the previous problem, if you look at the coefficient of variability here, look how small the standard deviation is compared to the mean here, and this is very practical to look at, right? I'm going to take this away in a second here, but what we're saying is here's a normal distribution of what we're looking at, okay, 12, 5, 6, let's say, and the first standard deviation is not down very far. It's only 43, let's call it just 44. Okay, so the standard deviation's up rounded up to 44 is very close. That standard deviation is not very large. In other words, 44 by 1256. Now the standard deviation before, the coefficient of variation was like pushing 50%, and here we have is equal to 44 by 1256 or something like that. It's 3%. Okay, so that's something that tells us about our data. Okay, so let me take that off. Just want to show what we're looking at here, and this dynamics of the dynamics of statistics is to push things around, and you can see the dynamics going on here, how it's behaving, how it looks. Okay, so this is probably a level up from I'm thinking any statistics you've had before. Okay, so sample size is equal to. Actually, I'm just going to copy this. Hold on. It's going to be the same thing. There's a little cheat. You have to be careful how you do this. And I'm going to change this to, let's come in here. I'm going to grab university so I don't misspell it. It's more than that. It also has where's the uppercase part of it and everything. Okay. So I'm just going to take that and put it right here. Control V. Right. That's how I avoid errors. So 25 to 24. They're pretty close. All right. So alpha, same and same. Just put it over there. Okay. Let's run the t-value. Okay. So it is equal to what? T dot inverse of probability is 1 minus alpha over 2 comma n minus 1 minus 1 2. Okay, so let me lock this down. 4. Okay, so then I can just drag it over here. Get our t-value. It's a little bit different. Okay, good. It's not much different. All right. Okay, so we're gonna combine some things here. So the upper limit, I'm gonna do two things at once, right? So this is gonna be x plus something. That's the upper, and then we're gonna do the lower, the same thing. That we're putting the entire error into this. Okay, so this is just going to be equal to t what times the standard deviation divided by the square root of n. So we're just doing it in one step here. And I put x. I should have put in the cell value. That's our mean. Okay. All right, and then I'm like typing those things over again, so I'm cheating a little bit. I grab the text. All I'm doing is grabbing the text. It's coming in here. It doesn't. Okay, and instead of plus, we're going to do minus. Okay, so our range is 1238 to 1274. Likely captures the mean of the population of liberal arts at a 95% confidence level. I think I could do that again. Control V. I hate to have to type that over again. Okay, we don't do this. 5 plus. Just type that one in. G10 times G6 divided by square root of our number. So I just shifted that over there. That's an attempt not to make a mistake while I'm doing it, but I probably could have entered as many mistakes doing that. All right. Control C, another little hack here. I'm just using the text of it. All right. And I need a minus. Change that to minus. Okay, so there's our ranges. All right. Hang on, everybody, because there is a problem coming up. I don't think it's this one coming up where they described something in the book that didn't exactly work the way they wanted it to. All right. So they cheat and they use a stock chart to look at whether these things overlay each other. Okay. So we have to set up when you use this kind of chart, it's one of the most restrictive, but one of the most often used ones with Excel's. If you're running your own portfolio and you're looking at shares and you're trying to figure out, what you should be investing in if you have your own portfolio going here, and it works a little bit like this. Okay, so this would be college type. You might not understand this at first. Okay, so this is going to be lib arts university. Okay, and we need to put our high. Let's see. Yeah, so we're going to do CI upper, confidence interval lower, and the mean. Okay, so the idea here is we're going to try to plot this. So we just need to do, you have to, for this kind of chart, set it up this way. All right. So I figure I'll do this a couple times. There's another following problem here where you have to do this. Okay, so let me take a look here. So we need to put the upper here, upper, Control C here. I should just make it this way, equals, I'm going to do it this way, equals the upper, and then I can drag that down. I think I can just do this. All right, so that just copied them all down, and we go get the means. Okay, so this is going to be equal to parts equals the mean of the university. Okay, get it? We've used those numbers before. All right. Now they say, I'm going to show you why it doesn't work. First of all, Control X. I want to move this over one box. I'm going to need this over here to make this work. Okay. So let me spread that out a bit. Okay, so what it says is grab this information like this and go to do insert, and if you look at it, you have this interesting little gizmo up here. So waterfall stock surface. Okay, so we want this stock. They wanted to use this high, low, close. I click it and I get this error. So I had to run off and figure out what was going on with this error. So I'll show you what happens. You have to fake this out. This is a kludge, all right? They don't say this in the book, so I don't know how they got it to work, okay? Temporarily, I'm going to move these out of there. I'm just going to put them over here so we remember what it's about. And I'm going to put in any date. This kind of plot is one of the most restrictive plots that they have in here, and you have to have a date in here. So I'm just going to use a couple, like 4. I'll use 4/9, 2020. You can use any date, prehistoric, future, whatever it is. And then I'm going to do 4/10. It's just to fake out the plot. Okay, so now I'm going to grab this, and this has to be a date, a legit date down here, these row headings here, just the way that it works, all right? I saw, there was no notes or anything about the fact that that didn't work in the book. Okay, so now we're going to do the same thing. We're going to go in here, and we're going to do stock, and look, it worked. Oh, yeah. Well, it only partially worked. I don't know. The kludge that I just had to take care of is part of a correction you have to do, but this is not plotting correctly. And I don't know what's going on. So you might have a slightly different version of Excel. All right. And so they've been sending out a lot of updates. This should have a diamond in the middle. We should be able to edit these things. Okay. So if I right click on it and should be able to edit it, but I'm not able to. Okay. And so there's not much I can really do. It's showing us the extremes. It's showing us the high and the low, and it should have a dot or a diamond in the middle. It actually should look a little bit better than this. It's like really weak with these little thin lines and everything. You can play around with them over here, but it still doesn't have the piece in here that says, where's your mean, you know? So our mean for this, our mean is going to be right in the middle. When you use it as a stock chart, this is really for a high price during the day. This is for the low, and then there's a closing. Okay, so it would be like a closing price might have been up from the lowest point of the day, or it might have been down from the highest part of the day, or it might have been at the highest part of the day. You know, the last 3 weeks in the stock market, a lot of times the close will be the low and the close will be the high. Most action happens in the last half hours when everybody's like going crazy like this. All right. Okay, so that's going to come up, and so what did we do that for? That should help us with one of the questions here is based on the above results, does there appear to be a difference in the median SAT scores? Well, you would know if there was no overlap. Okay, so the high end, which one was lower? Which ones are we looking at here? The high here was the higher numbers. It's actually kind of interesting. The upper and the lower. The upper is higher. It's kind of interesting. This is actually showing the opposite, that LibArts actually has a higher median, but this is the range. The confidence interval lies between the ends of the lines at a 95% confidence level, that the median for LibArts is between these 2 points. 95% chance that the median of the population is between these 2 points. 95% chance that the university is between these 2 points. Notice how this is a bit narrower. Okay, so our confidence interval was smaller for this. It was wider for the LibArts, but they overlap. That's the big point here, is that the low end, I think of that's the liberal arts. Do I have this right? Just want to double check that. Yeah, it's interesting. Yeah. Okay, so this is the liberal arts line, this is the university line, and there you go. Okay, and they overlap, so there's a potential that they're the same, that they're not that different. If these were out of the range, if the line was all the way down here or something like that, that means, well, you got a pretty good shot that they're different, and that's the end of that one. Okay, so problem 638 is very similar to the last one. I'll just let you figure it out. There's not really too many calculations you have to put in here. You just have to understand what these, it's comparing an A and B group inside a hospital. A is nursing, B is specialist. So we're comparing across subsets. Notice, okay. So we take a look at what it looks like for the confidence interval. Okay, so problem 639. This is more practice at calculating your predictive levels, upper limit. Okay, so the predictive levels, I will go over this one. Okay, so we'll have to run these things out. Sample. Okay, so what we're running is, we're going to run this at 95%, then at 99% prediction interval. Okay, so what is a prediction interval? What's beautiful now is there's a pattern setting up that you should be following here. Okay, so we're going to take x plus or minus, and here we're going to use t because it's over 30, but we use a t here because if you look at a typical table, they might run out to like a t, that n of e is equal to 120. All right, so we're going to use a t here. Okay, so it's alpha over 2n minus 1. Okay, consider that. Times what? Before we had, let's see, s over the square root of n. Now we're going to do something different. Okay, so it's x plus or minus our t statistic here times what? Times our sample standard deviation. Okay, but now when we do a predictive, all right, the confidence interval is going to be a lot wider by an adjustment that we make. Thank goodness we had these statisticians go before us, so we didn't have to derive all this and figure it out. All right, but it's going to be s instead of over square root of n that we had before. Okay, it's going to be 1 plus 1 over n like this. Okay, it's a square root, s times this. And what this should show is that we're starting out with a confidence interval that's including, it'll never go to 0. Okay, so before, when it was over the square root of n, as n got really large, this term all went to 0. So your error keeps going lower and lower and lower as your n goes up, as we would expect it to do. Okay, right? Your error will go down as you get closer to the population. Okay, but now what happens is it never goes below 1. Okay, so if n gets really, really large, this term goes to 0 and you have a square root of 1, essentially square root of 1. And so the minimum error is going to be your t times your standard deviation. So it's going to be some multiples of your standard deviation. Aha, okay. So that should simplify things a few ways here. Okay. So we have this is the larger file that's available for the problem. Okay. And so we're just going to let's look at how many samples there really are. It looks more complicated than it is. Number of hours per week in vehicle. Well, they have different kinds of vehicles. What is foreign or domestic, we're going to ignore. Satisfaction, we don't care about. Gender, age. There we go. There's hours per week in vehicle. Okay, so we need to take we're going to compare confidence intervals at the 95% confidence level of hours per week in vehicle and miles driven per week. So we're going to look at it at 95, and then we're going to look at it at 99. Okay, so our predictive interval here. Okay, so this is now the error for the predictive interval. Okay, so let's go take a look at that. Okay, so we have to run the general things. If you've got video speed controller, you could speed this up because this is things that we've done before, but I have to run through these. So this is going to be an average here. So it's Alt MUA. And I want this, and I do a Control Shift down arrow. It selects all of that. Okay, and I just jumped ahead here by I ran out the primitives. This is calculating. Nothing's different between the fact that we're doing a 95% predictive interval versus a 99%. The upper primitives are all the same. I just ran them out for us. You'll just notice that the alpha is smaller here, right? Okay, so let's do the T alpha, right? So T alpha, we have to remember, like, it's alpha over T of alpha over 2 with n minus 1. So we're going to do equals, what this before? So I'm just going to put this whole equation in here. We've sped it up a little bit from the earlier primitive type things we were doing in the earlier problems. Okay, so I just want my mean, sample mean. So this is going to be equal to sample mean plus, I'm going to put this in parentheses to make sure it doesn't get away from us. It's usually a pretty good idea to contain everything in there. So T times sample standard deviation times the square root of 1 plus 1 over n. There we go. I think our order of operations is all good there. Close it with our parentheses here. We get 18.64. Okay, so what we're going to notice, look how large that is. There's our sample mean, and it's 10. It came out that the error, right, was 18 minus 8 is about 10. The error is greater than our mean. It's huge, very large point there. Now watch out, we're probably going to get a negative number down here. Does it make sense that somebody drove their vehicle less than 0 hours here? Let's go through and take a look at it. Sample mean minus, and we're going to put that same function in there again. And I love typing all this out. So it's going to be this times the sample times the square root of 1 plus 1 over. Make sure you get the 1 over and close that out. Hang on a second, it doesn't like that. I'd rather find the problem myself than take their lead on it. Square root of 1. Did I not get enough there? Okay, that's I think all it was. Yeah, we got a negative number there. Look how wide that was. So I knew that 8 minus 10, the error is, I'm not explicitly showing the error here, but the error came out. Our upper limit is 10 larger than the mean. This is a huge margin of error here. And so we're going to do the same thing for the miles driven per week. Okay, I sped it up a little bit, or I paused while I filled this out. And you can see, T, of course, T doesn't change because we have the same number of samples. 50 people in here. Alpha didn't change for any of this. T does not change, but then our upper limit, because this is now notice we're doing miles driven per week, 8 hours and 502. So you can find out their speed if you wanted to figure that out, their average speed there. Okay, sample size, standard deviation. So here notice that the coefficient of variance right now, or variability, is like 300 over 500. It's like 60%. There's a very large standard deviation going on with this data with the miles. It's very large. 0.6 is very large. Roughly, that's what you get. All right. So we got to think about that. Because why? Because we're taking t times the standard deviation here, and we get this fantastically large number here. It's almost 1100. 1100 is the upper limit, and our sample mean is 500. We're going to end up, and yeah, we ended up with another negative number down here. So you have to consider that these are really zero. Okay, there is a lower limit on this, but we're not going to touch that right now. Okay. And then if we just run through it the same way for 99, you can finish the problem. I'm not going to finish it, but you can go through and finish this problem. Okay, and as we take a look at 641, very similar to the last problem, you're going to run this thing out. You can do, I guess you could calculate the confidence intervals and the prediction intervals here, I think, to answer the problem. It's very similar to the previous problems that we've done. I'm going to get on to the next couple of problems here that will finish this thing off. They're a little bit different. This one's the same as the last one. Okay, problem 642 here. Okay, we're giving some information about consumption of milk. And they're saying that the Trade Association figured out what the annual per capita consumption of milk is. We want to estimate that. So at 95% confidence interval, level of confidence is 95%. How many how many people do we need to talk to to understand how much milk they use to come up with a confidence interval plus and minus 0.52 from the mean, which we don't care about. They're just asking to prove a point here that to come up with the error, we just need what? The standard deviation of the sample and the number of people that we talk to here. Okay. So normally, we think about, I'm going to write it all out here. So x, that's your mean, x bar, x plus or minus your z of alpha over 2 times s over the square root of n. Okay, so we have this, and this being the error, okay, we know that we're not really, we don't really care about this right now, okay? We want to know the error is equal to this. It's x plus or minus the error, and so the error is 0.52. Okay, so 0.52 is equal to 1.96 times 6 divided by the square root of n. So we just have to figure out, solve for n here, right? Okay, so we'll bring square root of n over to the other side. We'll multiply both sides by square root of n while dividing by 0.52, 1.96 star 6 over 0.52, all of that squared. Let's see if it comes out. I'm just going to pause and then come back with the answer. Okay, as we return here, we've got a partial person. All right, we have 511.45 people. So how are we going to get that 0.45 people? Well, the minimum rounded up. Okay, so it's going to be 512. Okay, and that's what they're looking for from that. Okay, and then when we take it 643, it's almost the identical problem here, only what? We're not looking for median or median. we're looking for a proportion. Okay, so what was the equation for the proportion? Okay, so we are given. Okay, now earlier in one of the problems, I showed that if you run out the p times 1 minus p, right, it comes out as a function that looks like this between 0 and 100% probability. If you multiply these things together, it's not a half circle, but it kind of looks like this. Okay, and this is going to occur at where? This the middle is the highest point, and that is where p is equal to 0.5. All right, it's 0.5. And what is 0.5 times 1 minus 0.5 is 0.25. And so we didn't know what proportion is really selected. We just used the worst case scenario in this point of 0.5. I say worst case because what? This is the largest that p times 1 minus p ever gets. That's going to maximize everything under the square root. That's going to increase or maximize whatever the error is. Okay, so the error is equal to this part of it up here, right? X plus or minus the error. Okay, and so this is the problem where it's listed at one line in the book. You have to be kind of sharp on this, and then you just take it to say that p times 1 minus p is the most one is p is 0.1 is 0.5 here. So solve for that, solve for n. I'll let you do that work. I wouldn't take the fun of solving this away from you, but I kind of teed it up here. I always create a nice little table of the information so we can figure it out. All right. All right. Tease it up so we can solve it fairly straightforward. Okay. So all the best for this homework. And I hope that everybody tried to do the problems first before taking a look at the solutions. But there's some fine print in there, and the graphing that they talked about using the stock graph, the chart here, didn't work as they said, and you have to do that fake issue there. I'm going to go back to it. Where did it occur? Back here. What you can do afterward is you can just grab these actual labels and just put them in there, and it updates your graph with that. So, whoops, Control Z. So after you've actually created the chart, you can fake it out. It's kind of weird. At first, it looks to make sure that these two elements in here are valid Excel date format. So there you go on homework 6B.